But I have been traveling, so it's really takes forever to upload when you're traveling. So I have to be in my office, which has been kind of an entertaining thing. Okay, Brooklyn, right? Ah, I'm trying, guys. I really am. I'll know it, but the day you guys graduate, you know that, don't you? I know it the day you guys graduate. Okay. I'm going to switch over to the document camera. Hopefully the document camera works. Okay. This hasn't been, interestingly enough, this historically has been my problem room for ITV. And this semester, it's had its quirks, but it hasn't been too bad. It's been my other room over in Wilkin that's been a pain in the tushy. It's just been difficult. All right, so as we said, Physics 2 is a little different. And Physics 2 we do a whole lot of things trying to do it from a historical basis. And we've calculated so far, we've looked at the force on our charges. And it's a field force, not a contact force. And folks, one of the easiest problems on the exam was how does the electric field and how does the electric force go? Electric field, of course, is Q, E is equal to force. So if I do that, I get E is equal to the force divided by Q, which means it's K, Q, R squared. When you guys take your MCATs, your pre-vet exams, any of those exams, when in doubt, guess is 1 over R squared. Okay? Because we're about to hit the only thing that doesn't go is 1 over R squared. So you get a pretty good chance on that MCAT, it's going to fall off as 1 over R squared. So on that particular part of the problem, I think you have a lot of you that forgot that this right here means the square root of R. Okay? So it's 1 over R squared is how the electric field goes. So for the last 2 weeks or so, we have been kind of working through to get to a point where we're about to get here. And if you guys remember in Physics 1, we started out with, velocity and acceleration, and they were vectors, right? And then we said, all right, that's great. And then we get to force, right? So force is equal to F equal to MA, or it was equal to G M1 M2 over R squared. Now you see another 1 over R squared, which is why, when in doubt, on your MCATs, do the 1 over R squared answer. Okay? Because it's going to be a better than 50-50 shot. So we've got a lot of those kinds of things that we look at, but we got to a point that we started looking at, if I took a box and I applied a force to it, and we got it to move a distance, right? We talked about the concept of work. And one of the beauties of the concept of work and the concept of energy and work was what? What made these problems a heck of a lot easier than these problems? No direction. We got rid of the vector quantities, remember? We didn't have to worry about the fact that I had an x and y component. We did worry about we had an x and y component because we remember we looked at work like this. If I had remember the shopping cart? I always do the shopping cart problem, right? There's my shopping cart, my artistic abilities on a shopping cart. And usually we talk about the fact that the force isn't exactly the way we wanted it. This is the force that's doing the work, this is the force we're applying, so we're not getting the bang for our buck in terms of how much effort we're putting into it. But that came from the fact that work, we said, was the dot product or the scalar product of the two vectors, and that work ended up being something like this when I had a vector being applied. And we looked at that component in the direction in which we were applying the force. Well, we're going to do something similar, okay? Because we deal with a field force. We're going to deal with our field forces. And one of the things that we do when we dealt with a field force, remember gravity is a field force. So if I'm sitting here on the surface of the earth and I have a ball, gravity is going towards the center, right? Gravity is going towards the center, so we have an acceleration due to gravity. So we have a force that's pulling that ball to the center. We know that we had this force that was dependent upon the position that we had away from the surface of the earth. And that we call potential energy. And that was mgh. And the further h was away from the earth, the more potential energy it had. So we've looked at that. Well, now let's look at a similar situation. So we do all this stuff to define the electric field. And I've got a distance away here. So this is separated by a distance d. And I've got a negative surface here, and I've got a positive surface here. And if we looked at this, we know, because we've actually measured it in the lab even, that I've got a uniform electric field between these two plates. I've got my uniform electric field. And if I have a positive charge, okay, if I have a positive charge and I'm holding it in place, we know what it's going to do when I let it go, right? It's going to want to move to the negative plate, opposite to track. It's going to want to move to the towards the plate. I also know that if I pull this charge and I try to move it towards the positive plate, I'm going to have to do work, right? Because I'm going to have to overcome the natural field force that's sitting there trying to have that positive charge, because it's going to be like trying to move two north poles together. We know we're going to have to actually do work. So we're doing that same kind of thing that we did back here, except now we're doing it with charges. So we're now doing it with charges. Are you actually leaving that door open so we can go in and out from the outside?
Yes, ma'am.
Did you do it on the other side too? Oh, cool.
Well, I'm not supposed to, but I'm getting tired of hearing it.
Well, I'm telling you, it's a pain.
Yeah. Everybody having to walk around.
Yeah, not that I need my steps though. Yay! I'm so excited. It's the little things in life, right? Totally little things in life. So back to what we're doing. So work is equal to force times distance. We know that force in the case of our charge is QE, right? So now I can do that work that I'm going to do is going to be QED. So I've got QED, so I can actually do that work. And remember that we talked about the change in energy was equal to opposite the work. Because my favorite definition, we all know my favorite definition in all of physics is what? I know it's 8 o'clock in the morning, and I know it's cold. But you guys know my favorite definition. Come on, AJ. It's my favorite definition because when I give it out, it means absolutely nothing until we explain it. Has to do with work, and it has to do with energy.
Power.
Energy is what? Energy is the ability to do work. Now you knew it and you weren't saying it, right? All right. Okay, guys. I need some life in here. We may have to make you guys all stand up. Alright, so energy is the ability to do work. And this is what gives us our second law of thermodynamics, gives us a whole bunch of other things. And we also said forms of energy, right? We had forms of energy, we had potential energy. And in the case of this potential energy, we were talking about gravitational potential. We have kinetic energy, right? We have good old kinetic energy. And we talked about what other kinds of energy? You guys really wanted it this morning because it's cold outside.
Heat, sound.
We have heat, there's sound, light. But if I go out and everybody's got one of them on them, I'm pretty sure my artistic ability, we'll do the good old copper top. What's that? I put a plus and a minus. What is it?
Battery.
It's a battery. I even gave you the good old copper top. Does everybody know what a copper top battery is? What's the brand name? Thank you, Duracell. But we carry these around because these are filled with what?
Energy.
Yeah, they're filled with energy. Sometimes the obvious answer is the right answer. But we also call it something else. It's very much like gravitational because we stored it up, so it is a form of potential energy, and we're going to talk about electrical potential. Well, voltage is the unit. We're going to be looking at potential difference, and voltage is going to be our unit that we're going to end up with. Voltage is going to be our unit, and we're going to be out there. So electrical potential. So electrical potential, if I've got work here, right, electrical potential, and I want to do this, we're going to define our electric potential with a V, and that's going to be our change in energy divided by Q. And our change in energy is opposite work, so our electric potential then becomes just ED. Because if I do this as QED divided by Q, that cancels out. And so we talk about the potential difference. So if I go back to our handy dandy electric field, and electric fields are really easy to make, okay? Electric fields are really easy to make. We can look at, if this is our initial point, or this is point A, and then we've got a point B, we can look at our change in potential as V minus A, and that's going to be my change in energy divided by Q, and that's going to be opposite the work done, and this is moving it from here to there, okay? This is moving it back that way. AB divided by Q, okay? So we get this change in potential, and you guys actually measure, because potential is easy to measure. Electric field, not so much. Okay, electric field, not so much. So when you guys did your lab on this, so here's my plate, you had two lines like that. you actually measured equal lines of potential, right? You measured this. This might have been 1.5. This might have been 0. And this might have been negative 1.5. And we said that the field lines, or at least in your lab, it was discussed as the field lines were perpendicular. So if I put in my field lines were going to look like this. They're perpendicular to my potential lines. And when you guys did your ones around, say, one spot, you got electric potential look like this. And your field lines were perpendicular. And if this was positive charge, then we were radiating out. And the numbers would increase as I moved away from our dot. So we can actually measure potential, and from potential we can infer what the electric field looks like. So let's look at what we've got. So I've got the potential, or my change in potential. It's going to be the change in energy divided by Q, which is going to be negative the work divided by Q, which we already said, if this is QED divided by Q, that just becomes ED. So let's look at the units. So I've got the electric field is Newton coulombs. And distance is in meters. So I end up with this weird unit, Newton meter coulombs. But we know what a Newton meter is in terms of energy. That's a joule, and these are joule coulombs. And we define 1 volt is equal to 1 joule coulomb. All right, so I probably beat it into you figuratively all during Physics 1. That if I've got a velocity, it better be in meters per second. And if I've got an acceleration, it better be in meters per second squared. And then I had newtons, and then we had Newton meters for when that was torque. And we had Newton meters becoming joules, and newtons were kilogram meters per second squared. Our universe was not terribly complicated. And we said if you follow the units and do the unit analysis, you can be pretty sure you've rearranged the equation and you've done it right. And I beat on you, and I beat on you, and I beat on you, and I said, look at your units, because that's going to tell you if you've multiplied or divided right. You know, it's going to really, really help you out. Okay. If it weren't in my notes, I wouldn't necessarily remember that a volt is equal to a joule coulomb. And we're about to get units called Faradays. Faradays and coulombs are charge. I'm trying to think of the one for capacitance. Oh, Henrys. Henrys is inductance. So we get Henrys, we get Faradays, we get, volts, we get, the units start to get, and we get amps. The units start to get really kind of funky. And yeah, I can easily derive what the unit is for us because we're going through the derivation. But when we start working problems and we're dealing with amps and volts and Faradays and Henrys, I don't necessarily remember what all those subunit parts are. And your unit analysis gets a little complicated. So I'm just going to give you a heads up that your unit analysis gets a little complicated. You can still use it, but it is going to make life a little bit more complicated as we work through it. All right, so let's do a quick problem. We'll leave this part up here. So we know that negative work is going to be QE. And we can look at how much work does the electric charge do moving a 0.6, no, sorry, a negative 6.0 microcoulomb charge from ground to a point whose potential is 80 volts. So if we say ground, ground is going to say that the potential is equal to 0. Okay. Potential is equal to negative work divided by Q. And I think I left off the unit on something that doesn't look peachy dandy. Yeah, work is QED. Thank you very much. Work is QED. But if I do this, negative work is QV. Our change in potential, so our charge is negative 6.0 microcoulombs. Our change in potential is 80 volts, and that's going to equal my negative work. So I'm going to get my 6.0 times 10 to the minus 6 times 80 is going to equal the positive work because I took out the negatives. And this equals 4.8 times 10 to the minus 4th joules. Because this is, so I've got coulombs times volts, which is coulombs times joules over coulombs, which is going to give me joules. So if I do my unit analysis there, we get it. Now, we also use a term of energy called an electron volt. An electron volt is defined as 1.602 times 10 to the minus 19 joules. That's the charge on an electron. So 1 electron volt is that joules. And you'll see that around and around other places. And for those of you who are medical types, the x-rays are measured in electron volts. We use x-ray machines in terms of electron volts. So you'll see electron volts a lot more with medical types of equipment. Oh, speaking of which, guys, if you're headed to pre-med, University of Central Oklahoma has a medical instrumentation type degree. And they also have built a new kind of a medical type degree program down there. They will accept almost all of our classes. I just talked to the physics department, and they've got, through the physics route, you can go towards pre-med. And they've got a new office that's built, and I don't know if you guys know about it, but UCO does anatomy of human dissection because of the funerary services program down there. So if you're headed pre-med, you might look at UCO and might look at UCO for a variety of other things, because there's also the big forensic school. down there. So there's a lot of cool stuff that's going on. They've got a new group that they've got folks from the forensics department, folks from the physics department, folks from the chemistry department, and the biology department, all working in this new STEM center, doing a lot of cool things. So it's just another option for you for looking at pre-med, and it's cheaper. It's cheaper than OU. And for you baseball guys, it may be an easier baseball team to go on. So I know one of our guys, Kobe from cheer, he's going down there looking at it. So it's definitely an option if you guys haven't looked at it. I'm a UCO graduate from a long time ago. So, but something that just another option that people don't think about. Okay, so let's go back to that. Work now is equal to negative Q times our potential. So this is charge times electric potential, and this is QED. Okay, QED. And so now we can solve for E. Okay. If I solve for E, I get rid of my charge, and I get E is equal to negative VD. Now this is one of those cases where life becomes really, really cool, because if I've got two plates, I know the distance between these two plates, and as we said, we can measure the potential across these two plates. So I can measure the potential across those two plates. I know the distance between my two plates. I can calculate my electric field inside the two plates. It's super easy to calculate inside the field. So if I do this, now remember that we said an electric field has units of Newton coulombs. So we're going to do a quick unit analysis here. A volt is a joule coulomb, right? And that's divided by a meter, so I can actually do this as joule coulombs 1 over meters. We know that a joule coulomb 1 over meters is equal to a Newton meter coulomb 1 over meters. Meters cancel, and I get into a Newton coulomb. So an electric field can either be represented as Newton coulombs or as in volt meters. So you can see the electric field in two different units, that they'll give it to you in two different units, but they're actually going to be equivalent. Totally equivalent. And that's why I said when you start getting into electricity, your unit analysis gets funky. Okay? Gets funky. All right. So electric field is volts there, right? So if I do this, let's do voltage. Let's come back here. We get voltage is equal to ED, or the magnitude is equal to ED, right? We know that the electric field, because we played with it so much, is KQ over R squared. And if I'm doing the distance and I'm doing this interpretation, that's going to be R. One of these R's cancel out, and now I'm going to be KQ over R. So this is one of those cases where I'm not going to go as 1 over R squared, I'm going to go as 1 over R. So what happens is that my voltage is going to be proportional to 1 over R, and if I look at that graphically, and for this is R, my voltage is going to drop off as 1 over R, and this is for Q is greater than 0. This is for Q is less than 0. And it's at infinity, it's approaching 0. Okay? At infinity, it's approaching 0. Now, this is one of those cases that for voltage, we're going to have to keep track of sign. Because if I look at this, whether I'm a positive or a negative charge, we're going to have to keep track of sign. Now, it's going to make life easier for us, and it's a little different than when we have potential energy because I didn't have to worry about a change in sign. I will have to deal with that change in sign. So let's look at a quick problem here. I'm going to be given a charge of 10 microcoulombs. And and we're going to look at the electric potential at 0.1 meter away. So we want to know the electric potential at 0.1 meters. So I've got my positive charge, and we're going to be out here, and we want to know V at this point. And this is 0.1 meter. Well, that's easy enough. Voltage is going to be KQ over R. And this is K is 9 times 10 to the 9th Newton meters squared, coulombs squared. 10 times 10 to the minus 6 coulombs divided by 0.1 meters. And if I plug that into the calculator, I get 9 times 10 to the 5th. Meters cancel, coulombs cancel. I get Newton meter coulombs, which is a joule coulomb, which is a volt. Now, if the charge were a negative 10, the number's going to be the same, but I'm going to have a negative 10 times 10 to the 5th volts. So it's fairly easy to calculate. So now if we look at the change in potential from a point A to a point B, okay, change in potential to a point A and point B, we can do that change in potential is B minus A, and we're going to say that that equals 20 volts. And we've got a charge of 2.2 times 10 to the minus 6 coulombs. We can calculate the change in potential. We're going to multiply this times this, which is equal to our change in potential energy, which is going to be Q VB minus VA, and we would just multiply this times that. And if I do that, that number works out to be, just so you have it, 4.4 times 10 to the minus 5 joules. So my change in voltage is going to equal a change in potential energy divided by Q, which is going to equal a change in the work divided by Q, which gets us back to negative EB cubed. So when you guys start working these problems, don't make them harder than they are. So let's do something like this. So I've got my apparatus set up here. This is a positive plate, that's a negative plate. We're told that the distance between the plates is 10 centimeters. We know that the potential difference, and a lot of times with the way they'll do this, is they'll put a little thing like this with a V in it, and we're told that the potential difference is 50 volts. Let's calculate the electric field. The electric field is going to be the voltage divided by the distance, which means that I'm going to have my 50 volts divided by my 0.1 meters, and I'm going to have a 5 volt meter electric field. So now that we can do electric fields, and remember, we can do electric fields and we can do energy. So 1 EV is equal to 1.6 times 10 to the minus 19 joules. We can do similar things that we've done before. If I know the potential energy, and we say all that potential energy converts to kinetic energy, we can look at 1/2 mv squared. And if I have a proton that has a 3 kilovolt energy, and we know the mass of the proton is 1.6726 times 10 to the minus 27 kilograms, we can figure out how fast that electron is moving. V squared is going to equal 3 times 10 to the third electron volts divided by my mass of my proton. And if I plug that in, I get 2.87 times 10 to the 11th meters squared, second squared. And if I take the square root, I get about a 5.4 times 10 to the 5th meters per second. And if you're a higher energy physicist, these are calculations they're doing all the time, because when they're atom smashing, that's what they're doing. So work is the change in potential energy. We get the change in kinetic energy. We can use those work energy theorems, just like we did in Physics 1. And we don't have to worry about direction anymore. We don't have to worry about direction anymore. It makes life a lot easier. So you guys got questions? You guys do good? Staying awake? Staying awake. All right. So let's look at it a little differently. Change a little. And this is always those fun things. We're going to do one of those conceptual problems. I'm going to bring in a charge. So we've got a positive charge. That's a 20 microcoulomb charge. And they've got a point P that's, the distance between point P is 0.1 meters. We want to know the work. We're going to bring in a charge, then this charge is sitting out way, way away from way. So we're going to say it's at infinity. And that charge is a 2 microcoulomb charge. And we want to know the work done to bring it from infinity to right next to our 20 microcoulomb charge. So the work done is going to equal my change in potential, right? And that's going to equal VB minus VA. And that's going to be our, and this is B and this is A. So this is going to equal charge times K, Q, R, B minus K, Q, R, A. Well, the K and the Q are the same, right? So we can look at that. Hang on. I'm finding all kinds of fun stuff. No, I'm doing right. Doing okay. Doing okay. All right, now this Q is this one. This Q is this one. So we're going to draw my picture different so we can keep track. This is the charge that I'm bringing in. That's the charge that I'm doing this side. So I can get Q, K, Q, and I have 1 over RB minus 1 over RA. Now, if I've got 1 over a really big number, we can approximate that as 0. Because 1 over a very big number approaches 0. I want to do it that way, it's approaching 0. Now if you want to prove it to yourself, 1 over 99, let's do it. One over 99 is equal to 0.010. 1 over 9,099 is equal to 0.0001. So as I get this number gets bigger and bigger and bigger, it's going to approach 0. So if I'm coming in from infinity, this just becomes 2 times 10 to the minus 6, 9 times 10 to the 9th, 20 times 10 to the minus 6, divided by 0.1, and that equals 3.6. And if you do the unit analysis, you get Newton meters, and so it's 3.6 joules. And we can do a lot of different problems that way, so let's do another one real quick, just to keep everybody honest. I've got a charge here that's 20 microcoulombs. We've got a little charge that's 3 microcoulombs. It starts at 1.5 meters away, and it's going to end up at 0.5 meters away. So we're going to bring it in from 1.5 to 0.5. We're going to do W is equal to QVB minus QVA. That's going to be my 20 times 10 to the minus 6. I've got my K out here and my Q out here, which is 3 times 10 to the minus 6. And then this becomes 1 over 0.5 minus 1 over 1.5. So I'm going to end up with 9 times 10 to the 9th, because that's the K. I end up with 3 times 20 is 60. 60 times 10 to the minus 6. over 0.5 minus 1.5. And that will end up being 0.72 joules. Okay. Now, this is why we like working in potential. Because remember when we were calculating electric fields, when we took a problem that looked like this, I had a charge here, 8 microcoulombs. I have a charge here of 2 microcoulombs. And I have a charge here of 4 microcoulombs. This one is 3 centimeters apart. This one is 6 centimeters apart. And when we did electric fields and we did electric fields and we did forces, I wanted to know something about this point P up here, I had to use my vectors, right? I had to calculate the actual magnitude, and I had to look at the direction, and I had to keep track of my vectors, and it was a pain in the tushy. Well, now these are all scalars. So if I want to know the potential at this point, I just got to find the potential at this point for the potential due to this charge, the potential due to that charge, and the potential due to that charge, and add them together. I don't have to really worry about it so much. So let's go ahead and do that. So we know that potential in general is going to be KQ over R. So I got to figure out my R's, right? Well, this one's easy. That's going to be 6. This one's easy. That one's going to be 3. It's this R that's going to be a little complicated, because this is going to be an R that I got to know. Well, that's easy enough, because that's just going to be the square root of 6 squared plus 3 squared, which is going to give me the square root of 45, which is going to give me 6.7. So now I just got to do V8 microcoulombs. This is going to be 9 times 10 to the 9th. 8 times 10 to the minus 6. And we are at 8 microcoulombs, it's 0.06 away. And that gives me 1.2 times 10 to the minus, or 10 to the 6th. I do it for the 4 microcoulomb. I get my 9 times 10 to the 9th. 4 times 10 to the minus 6. And I'm 0.03 away, gives me 1.2 times 10 to the 6th. That just happens to be fortuitous. The other one is at 2 microcoulombs. It's going to give me my 9 times 10 to the 9th. And my 2 times 10 to the minus 6. And now that's 0.067 away, and that's 2.69 times 10 to the fifth. And now we just look at the potential total, and it works out that I have 1.2 times 10 to the sixth plus 1.2 times 10 to the sixth plus 2.69 times 10 to the fifth. And when I add all that together, this ends up being 2.67 times 10 to the sixth. Now, if it turns out that this is a negative charge, I put in a negative sign here. I have to keep track of my sign charges in order for this to work. And if I do that, so if I put in a -2, I get the volt total is going to be the V8 plus V4 minus V2. And this is if the 2 microcoulomb charge is negative. And if I plug in those same numbers, I'm going to end up with 2.13 times 10 to the sixth volts. So now I don't have to calculate my vector components, I just have to calculate the magnitude. So using the scalar is really going to help me out. It's really, really going to help me out. Does that make any sense? Certainly makes the problems a lot easier. Makes the problems a lot easier. So let's do this one. I've got a charge of minus 15 nanocoulombs. I've got a charge of 27 nanocoulombs. This is my point A. And we're told that this is 0.02 meters, and this is 0.02 meters. I want to find the potential at A. Well, this is just going to equal the potential due to my negative 15 nanocoulomb charge plus the potential due to my 27 nanocoulomb charge, which is going to equal K, Q, R, negative 15, plus K, Q, R, 27. So I can factor out my K, which is 9 times 10 to the 9th. And then this becomes negative 15 times 10 to the minus 9 over 0.02. Plus 27 times 10 to the minus 9, 0.02. Plug that into the calculator, and I get 5.4 times 10 to the third, and that's in volts. If I want to find it at point B, where this is 0.01 and this is 0.01, I want to do the exact same thing, except now I put a 0.01 in there, V total at B is gonna be 9 times 10 to the 9th, 0.01, because they're both 0.01. Negative 15 times 10 to the minus 9 plus 27 times 10 to the minus 9. That number gives me 1.08 times 10 to the 4th volts. Making sense? Until you do one? So those same types of problems that we were doing with electric fields, forces, becomes a heck of a lot easier when I'm trying to calculate potential. So we're gonna take this a little further. And now we're going to build a device. So I have a parallel plate. We're going to apply a voltage across it. It's got a distance d here. This is a positive side and this is negative side. We've already shown that the electric field is my change in potential divided by the distance. And we already know that the potential is equal to the potential energy divided by Q. So now I get the electric field times the distance is equal to a change in potential. And we know the electric field is K, Q, R squared D is equal to V. This, so I'm going to rearrange it. Okay, I'm going to rearrange it so that K D R squared times my charge is equal to the voltage. This term right here is dependent on the configuration. So it just depends on my configuration here. I can build this any way I want to. I can build this any way I want to, but this term is going to be dependent on that. So I'm going to rearrange things here. And I'm going to call this a constant dependent on the configuration is the voltage divided by the charge. And this ratio, the ratio of the magnitude of the charge to the magnitude of the potential difference and basically what that's saying, this ratio, we're going to flip it over and I've got QV. So that ratio right there, we are going to define with a big C in farads. So Q over V, C over V is going to be a farad. We're going to give it a name and we're going to call it capacitance. Okay, we're going to call it capacitance. Basically, what this device will do is it'll allow us to have a uniform electric field, and it's going to store charge. Capacitors are going to store charge. Now, capacitors, batteries are kind of like capacitors because batteries store charge. They're not quite the same, but you can think of a battery as a type of capacitor. my capacitor is gonna store charge. The problem with my battery or my capacitor is if I left it out there for a while, it's gonna, it'll dissipate off. Now, can anybody think of devices that are capacitors? Besides the fact that a capacitor is a device. You all have one on you, I'm sure. Now, do you remember the old disposable cameras that you would get for weddings and stuff? And it has a little flash on it, and you charged up the flash. What did you hear when you charged up the flash? Yeah, it's got a whistle to it. You're charging up the capacitor. Your flash bulb, or flash, a camera flash, is probably the easiest example of a capacitor. Okay, we're storing charge, which when we discharge it, we're going to get the flash of light, and we're going to be able to have that energy. Your keys on your computer, those are capacitors, because when I touch the two plates together, it creates an electrical signal that allows my computer to know which key I pressed. So we use capacitors to store charge in the system. That's exactly what we do. So we have capacitors, and so if you think about it for a second, and the reason I bring up the flash bulb is because when I deal with my circuit, and what we'll end up seeing is if I close my circuit, what we end up doing is we charge the capacitor before, if I close the circuit, before things can flow in my circuit, I gotta put charge in my capacitor. And it's gonna take a little bit of time. So when we're dealing with a capacitor, capacitors are gonna be like this in a circuit. So I'm gonna take a little bit of a stop here and kind of do the symbology of things that we're gonna look at. So this is gonna be a capacitor. And this is gonna be a battery. Because capacitors and batteries are similar, that's capacitor and battery. And generally the large side is the positive and the small side is the negative. So this is our battery. We're also going to start seeing, if you haven't already in lab, this is a resistor. You'll see things that look like this. This is an inductor. A switch is usually represented like this, and this is an open switch. And sometimes they will draw it with a little arc to it. Sometimes you'll see a capacitor drawn this way, and that's what's drawn on our multimeters. The multimeters, if I'm in capacitance to read capacitors in my multimeter, that's how it's drawn on the multimeter. So I've got an open switch, and a closed switch is usually represented like this, so that you can see that the switch is closed. So we will have these symbols that we will use to represent our various electrical devices as we start moving forward. And Ben Franklin got it wrong, remember, and this is one of those things that we're going to worry about. So just from a symbology point of view, if I have a circuit, and we're going to start with circuits that look like this. So this is going to be a circuit with a capacitor in it and a battery in it. The current, which we will define here fairly quickly, probably on Friday, goes positive to negative, and you can represent the flow around my circuit. That's why I said Ben Franklin got it wrong, and we're all paying the price, because we know what's really happening is what? The electrons are moving, not the protons. So we have those things there. So hopefully that will help as you start reading through the chapter and looking at things for our symbology, and if you want to start working ahead. So we're going to get to a definition real quick. So we've got our parallel plate. We know the voltage across the plate. We know its distance. And we call these parallel plate capacitors, and so we can do ED is equal to my change in potential. And we can look at my change in potential over Q is equal to some constant. We also know that I'm doing forces in my other class, so we get the electric field, and we saw this previously as an example to the problem for two parallel plates and using Gauss's law, which is the whole point of what we try to get to so that we can start explaining how these devices work, is that I can look at my surface charge density divided by the permittivity of free space. Okay? And we know that my surface charge density is just really the charge per unit area. So I got that lovely. And now I'm going to plug that into this up here. So I'm going to get Q over A, 1 over epsilon. The separation of the distance is equal to my change in potential. I'm going to take the Q over here, so now I've got d A epsilon is equal to this, my change in potential over Q. This is the value of my constant for my device. So if I'm doing parallel plates, I know the area of my plates, I know the separation apart, or part it is, and I know the permittivity of free space, and we've already defined this as capacitance. We can do a variety of different things. Now, one of the things that we can do is, this is permittivity of free space, i.e. air. I could put something in here, some other material in there, and we can do this, and then we can put something that we call a dielectric constant. Dielectric constant, and so our capacitance in general is going to be a dielectric constant times the capacitance in air. So my capacitance really becomes this dielectric constant, the area, permittivity free space, and D. Because we define, this is actually 1 over C, sorry. That's 1 over C. Because we already had talked about it. And that is based on configuration and how I build it. Okay? And there's a table of these in your book, depending on the problem that you want to work on. I'm going to stop there because then we're going to put the capacitors in series and capacitors in parallel. And we'll talk about that. On Friday,